All right, so here's what he starts out with, this what he calls this simple example. We have a Watts-Storgatz graph with 1,000 people.
Okay.
And we don't have to worry about these other parameters for now. So the first thing he does is this simulation with the SIR model. Do you remember what the SIR model is and what that's looking at?
It was susceptible, infected, and recovered or removed.
Okay. I'm going to actually make this just a little larger so hopefully it shows up on the screen a little better. Okay.
So it just basically kind of takes you through the outbreak of the disease until it's done.
Yeah, and on this one, he's, if I remember how this one worked up here, he's assuming that each person has infects 1/2 a person on average in their steps. Although we should probably verify that that's true.
I mean, if they infected half a person on average, would this just be going down all the time?
Well, let's see. So next we run a simulation on this network with the same exponential distribution with a mean of 0.4, modeling the number of outgoing meetings for each agent. Okay, so there we go. So each agent on average meets 0.4 people each step. The distribution of recovery times being an exponential with mean of 7, and there are 10 random agents initially infected.
So it takes 7 steps to get from infected to recovered.
That's right. Okay, so here's what it looks like with that. And then he looks at it lots and lots and lots of different ways, which is actually really cool. So this is a graph that shows instead of the time step and the number of agents infected, not infected, and susceptible, this is a graph just showing the fraction susceptible versus the fraction infected. And so there's lots of different ways to look at things and gain information out of it. And he actually spends a lot of time looking at these phase plots, which is really interesting. And this is plotting the different ways the infection might evolve, looking at it from this kind of graph, which can be very useful, although it's not the normal way we would look at it. But you see with a high fraction susceptible, what you do is initially you move up. So the fraction susceptible is decreasing as people get infected, and the fraction infected is moving up. So you move up until you have very few susceptible, and then the number infected declines. So that's it. It's just a different way of looking at the dynamics of an infection.
Okay.
But then he does something really cool. And he looks at changing the number of people you meet on average.
Okay.
So we might guess that one of the most important variables is the mean number of meetings per agent per step. So how many people do you meet every day or whatnot, which is essentially the mean infection rate. We can control this by altering the distribution of meeting counts. For now, we'll give every agent the same distribution and just change the mean, simulating a homogeneous population. Okay. So the neat thing about this, and I'll summarize it in this plot, is when you meet a very small number of people per day on average, and remember this only starts with 10 people infected out of 1,000. What do you see happening in this plot here? Maybe I should start with one where it's a little bit more what we're used to seeing. Okay, so the blue is what?
Blue is the susceptible people.
This is infected.
Blue is infected.
I think
Green is recovered.
Recovered.
Yeah.
And orange is?
Orange is the susceptible.
Susceptible. Okay. So when I meet a very small number of people per day, what happens?
Let's see. It doesn't look like many people get infected.
So like the infections don't even get started.
Yeah. So even though a small number of people start with it, it doesn't spread through the population.
Yeah.
When I meet a large number of people per day,
it seems to spread very quickly through the population.
Yeah. But there's this transition area down here where very suddenly, from meeting 0.2 per step to meeting 0. Call it 3 per step, where it goes from almost no one getting infected to eventually the whole population gets infected.
It's a very.
So it's amazing how sensitive it is.
Mm-hmm.
And so he plots a graph about that down here, showing, based on the meetings per agent per step, up to about 0.2, the infection doesn't spread. That's because he's graphing the eventual total infected here. And also in blue is the peak infected.
Mm-hmm.
But above this sort of critical threshold, what happens?
It jumps really fast, and then you can't really, at this point, it's about 0. Maybe 3.5, and then basically everybody is going to get it at some point.
Yeah. So it's really fascinating that you kind of have this all or nothing property.
Yeah.
All right, so let's look at one last thing.